You know, in physics, some of the words we use every single day can have these surprisingly specific and, well, different meanings. Take distance and displacement. They sound almost the same, right? But they actually tell two completely different stories about an object's journey. So let's dive in and really break down the difference.
Okay, so instead of just throwing a bunch of equations at you, let's start with a simple story. Think of it as a little puzzle, set right inside a classroom, that'll help us see how physicists really think about motion.
So picture this. We have a student, and they're just sitting at their desk. This desk is their home base, their starting point. For now, they're perfectly still. All right, now the student gets up. They walk in a perfectly straight line, 5 meters, right to the classroom door. Then, they immediately turn around and walk that exact same 5-meter path straight back, ending up right where they started. A perfect little round trip.
So here it is, our big puzzle. How far did that student actually travel? Now your first instinct is probably to say 10 meters. And you know what? That's a great answer. It's one of the right answers. But in physics, there's another answer that's just as correct, and that's what we're going to unpack.
To really solve this, we need to get precise with our words. And in physics, that means we need to clearly define 3 key ideas: position, distance, and displacement.
First up is position, and this one is about as straightforward as it gets. It's simply where an object is located at any given moment. You can think of it as a dot on a map. So the student's position was at the desk, then was at the door, and then it was at the desk again. Easy enough, right?
Next, we've got distance. Now this is probably what you were thinking of when I first asked the question. Distance is all about the total path you've covered, every single step you took. It's like the odometer in your car. It just keeps adding up no matter which direction you're going.
And finally, we have displacement. This one's a little different because it's all about the change. See, displacement doesn't care about the long, winding road you took. It only cares about the straight line between where you started and where you ended up. It's the shortest, most direct route from your starting point to your finish line.
All right, we've got our definitions locked in. Now we can go back to our student in the classroom and see exactly how these ideas give us 2 totally different but equally valid answers.
So you can see here, we're really using 2 different ways of thinking. When we calculate distance, we're adding up the whole journey, piece by piece. But for displacement, we're just comparing the final location to the initial location. 2 different processes for 2 very different concepts.
Let's do distance first. Remember, distance is just the total ground covered. The student walked 5 meters to the door and then walked another 5 meters to get back. We just have to add those 2 parts together.
So, 5 meters plus 5 meters gives us 10 meters. The total distance traveled is 10 meters. That is our first correct answer. It's what a fitness tracker would tell you.
Okay, now let's completely switch gears and think about displacement. Here, we're asking a totally different question. We're asking, how far out of place are you from where you began? The journey itself, the path, it doesn't matter at all.
So think about it. The students started at the desk, they ended at the desk. Their final position is identical to their initial position. So, what was the net change? There wasn't one. Their displacement is 0 meters, and that is our second perfectly correct answer.
So, how can this be? How can you travel 10 meters, but your displacement is 0? Well, the answer comes down to one absolutely fundamental concept that separates these 2 ideas: the importance of direction. This brings us to 2 of the most important categories in all of physics: scalars and vectors. A scalar is pretty simple. It's just a quantity that has a size, what we call a magnitude. Think about things like temperature or maybe your own height. A vector, on the other hand, is special. It has both a magnitude and a direction, things like force, or, as we just discovered, displacement.
So here's the bottom line. Distance is a scalar. It's just a number. It asks, how much ground did you cover? And the answer is 10 meters. Simple. But displacement is a vector. It needs a direction. So if we say the walk to the door was, let's say, plus 5 meters, then the walk back from the door has to be in the opposite direction. It has to be minus 5 meters. And what happens when you add a plus 5 and a minus 5? They cancel out. You get 0.
You know, really getting the difference between a scalar like distance and a vector like displacement it's a game changer in physics. It unlocks a whole new, more powerful way of describing the world around us. And it leaves us with a pretty interesting question to chew on. If just adding direction can completely change our idea of how far, what do you think happens when we start applying it to the idea of how fast?